In this video, we'll discuss the fundamental theorem of calculus, the theorem that allows us to evaluate definite integrals for many functions and shows us a connection between integral calculus, solving our area problem, and differential calculus, solving our tangent line problem. The fundamental theorem of calculus will allow us to show that the integral of some function f of t dt from a to b is equal to f of b minus f of a for a function big F, where the derivative of this big F function equals our little f function that we're integrating. We've already shown this is true for power functions. We know this is true for, say, x to a rational power dx, that this is b to the p plus 1 over p plus 1 minus a to the p plus 1 over p plus 1. We'll now see how to show this is true for all continuous functions little f. We'll start, though, by reconsidering our area function, big A of x, as the integral from little a to x of our function little f of t dt. What we suspect is true is that a prime of x equals little f of x. But we haven't proved this for all possible continuous functions f. We'll now see how to sketch that proof. Here's a graph of a function little f of t. We define the area function big A of x to be the integral from little a to some value x of our function little f of t. We've labeled this b here, but it's the same idea. As b increases, the area increases in our case, and so we can find the rate of change of that area, which will be a prime of x. Whenever we compute a derivative of a function that's unfamiliar, we go back to the definition of the derivative. Now, what does a of x plus h minus a of x represent? We can think of, say, capital A of little b as this area, and then capital A of b plus h would be all of the green area plus the red area. So the difference between those two values would be this red area right here. Now, how could we estimate that? If we build a rectangle with height little f of b, the area of this red region that we want is approximately equal to the area of this shaded rectangle, which has a height of little f of b and a base of h. So we can approximate this value in our limit by the height, little f of b in our graph, or x here, times the base of the rectangle, h. Now we cancel this and we just get f of x, which is what we wanted to prove. We now have this conclusion of the fundamental theorem of calculus, or what we'll call part 1 of our fundamental theorem. This graph provides us with an idea for a proof. There's some technical details we have to worry about, but this graph should help convince you that the fundamental theorem of calculus is true. What this means is the derivative of our area function is our integrand, little f, so our area function, big A of x, is an antiderivative of f of x. A consequence of the first part of the fundamental theorem of calculus is the second part of the fundamental theorem of calculus. We know that our area function, a of x, the integral from little a to x of f of t dt, is an antiderivative of our integrand little f. But by a corollary to the mean value theorem, we know that this particular antiderivative of little f must differ from any other antiderivative of little f by a constant. So if f is any antiderivative of little f, this statement must be true. Now, let's be clever and plug little a into this equation. because we're integrating from little a to little a, this expression here must be 0. So big F of a plus c must be 0. That tells us that c equals negative f of a. This tells us that the integral from little a to x of f of t dt must equal big F of x plus c, which is now negative f of a. And if we replace this x with a fixed upper endpoint b, we get this statement of the second part of the fundamental theorem of calculus. In practice, we'll use this second part of the fundamental theorem most often, and we'll use it to evaluate definite integrals of functions. Let's look at a couple examples. If we want to find the integral from 1 to 3 of x to the fourth plus 5x dx, all we need is to think of an antiderivative of this function. It doesn't matter which one. We'll see why in a moment. So let's think, what function might have a derivative equal to x to the fourth? Well, probably something related to x to the fifth. If we guess x to the fifth, the derivative of this is 5x to the fourth, which doesn't quite match, so we might guess 1/5 x to the fifth. And then an antiderivative of 5x, we might guess that to be 5/2 x squared. When we guess an antiderivative, we always want to at least mentally take the derivative of this expression to double check that we get back our integrand. We now need to evaluate this from 1 to 3. We might, if we want to be careful, write x equals 1 to x equals 3 here just to be safe. So we get 1/5 times 3 to the 5th power plus 5/2 times 3 squared, and then minus 1/5 times 1 to the 5th power plus 5/2. I'll let you simplify that if you want, but this is our numerical answer for the definite integral. If instead I had chosen an antiderivative of 1/5 x to the 5th plus 5/2 x squared plus 17, what would happen now? Well, I would plug in 3, then I would plug in 1, and I would subtract these two quantities. But when I do so, this 17 minus that 17 will cancel, and I'll get the same answer as before. This procedure works as long as we can think of an antiderivative of our integrand. For example, if I have the integral from 0 to pi over 4 of secant squared theta d theta, and remember the variable here doesn't really matter as long as it agrees, I just need to think of a function whose derivative is secant squared theta. And you might remember from differential calculus that the derivative of the tangent function is the secant squared function. So we could use tangent of theta as our antiderivative. So we get tangent of pi over 4 minus tangent of 0, which is 1 minus 0, and our answer here will be 1. To see if our answer is reasonable, we might graph the function secant squared theta from 0 to pi over 4 and examine this area underneath. Our computations show that this area should be equal to 1. And if we take this little triangular type region up here and we were to put it down here, we could believe that this part of the region here would fill out this square and give us an area of 1. That doesn't prove our answer is correct, but it makes us more confident that we've computed the right answer. Although we use the second part of the fundamental theorem of calculus more often, we'll occasionally have use for the first part. For example, we might define a function, capital F of x, as the integral from 1 to x of t to the 4th power dt. If for some reason we want to find the derivative of this function, big F, we could work out this definite integral as a function of x and then take its derivative. Or we could use the fundamental theorem of calculus that says that this must be equal to x to the 4th power, the little f at x. If we had a function capital G of x that was the integral from 1 to x squared of t to the fourth dt, we can't apply the fundamental theorem of calculus directly because we have an x squared as the upper endpoint of integration. But we can think of this as a chain rule problem. This is just our previous big F evaluated at x squared. So g prime of x equals big F prime of x squared times 2x. But big F prime was just the fourth power function, so this becomes x squared to the fourth power times 2x, or if we want to simplify it, 2x to the ninth. You could also work out this definite integral using the second part of the fundamental theorem of calculus and then take the derivative, and you should get the same answer. What if we had a function h of x equals the integral from x to 10 of cosine of t dt? Again, we could work this out with the second part of the fundamental theorem, or we could be a little bit clever and use the first part. We could rewrite this as negative the integral from 10 to x of cosine of t dt, so that we have x in the upper endpoint spot, and then we could take the derivative and we would get negative cosine of x. And if we came up with yet another function, call it b of x, that was the integral from x squared to x cubed of t to the 20th power dt, we could rewrite this as the integral from, I don't know, let's say 1 to x cubed of t to the 20th dt, plus the integral from x squared to 1 of t to the 20th dt. It doesn't matter what this number is. It could be 11 if we wanted it to be. Now I could flip the endpoints of integration here in the second integral. And I could apply the first part of the fundamental theorem of calculus together with the chain rule to find the derivative of this b of x function. So this would be the 20th power function with an x cubed in here times the derivative of this inside part, 3x squared, minus the 20th power function with an x squared in here times the derivative of the inside part, 2x. We could simplify this if we want, but that will be our answer. This more general version of the first part of the fundamental theorem of calculus is sometimes called Leibniz's rule. Here's our lower function, g1 of x, our upper endpoint function, g2 of x. If you prefer to use this formula, by all means do so, or you can think of any problem of this type as simply a combination of the first part of the fundamental theorem and the chain rule. Next time, we'll begin investigating some of the applications of definite integrals other than simply finding the area under a curve.